Hello and good day everybody. In today's video lecture, we would be discussing about how we would be assigning loads onto our structures in STAAD. So our example here is to be a 3-story residential building with roof deck located in Baguio City. And we will be designing such to be a special moment resisting concrete frame. And we would be making use of the model that we have generated in the previous couple of pre-recorded video lectures or the previous modules. And that is to be this one right here. But before anything else, guys, we would be having a couple of disclaimers first. So the first disclaimer is that we wouldn't be assigning wind loads in this particular video. So that will be discussed in the videos to follow. And as for the second disclaimer, so disclaimer number 2, the structural plan is to be a fictitious one. So this model right here is to be a fictitious one. So this model was just created for the sake of teaching the fundamentals of STAAD on how we would be assigning your properties, your material specifications, supports, and loading conditions. So with that being said, guys, whatever breach in the National Building Code is to be observed in this model right here, if any, was not taken into consideration. So once again, this model right here is to be a fictitious one. Okay, so once again, our topic for this pre-recorded video lecture is how we would be assigning our loads into our structure. So when you are to assign loads into your structure, you must first know these things. So number 1, of course, you must know what load category or what load case it belongs. So load case. So this is to be it. So load case. So what does this mean? So is your load a dead load, a live load, a wind load, earthquake load, or whatsoever? So what load case does it belong? And after which, the next thing that you would be asking yourself is that what is to be the magnitude of the load? So magnitude. Is your load, let's say, 5 kilonewtons? Is it a concentrated load? 5 kilonewtons? Is it, let's say, a line load? Let's say 2.9 kilonewtons per meter? Or maybe a pressure load? So maybe your live load is to be 1.9 kilonewtons per square meter or whatsoever. So that is for numbers 1 and number 2. And for number 3, guys, how is it transmitted into your structure? So how? So is it a joint load? So for your joint loads, I would be explaining this to you later, but this is pretty much straightforward. Is it located in your joints? Is it located at your members? So may it be a member load? Or maybe let's say it is to be a floor load? And whatsoever. And lastly, guys, this is for number 4. So I'm sorry as if you cannot see what I am writing right now. So for a while, so I would just be hiding your Excel first. Okay, so there. And for number 4, guys, in what direction do they act? So is it directed at your global axis right here, or maybe is it located, it is directed to the local axis of the member. So this is to be the global axis, and the local axis would be dependent upon the direction of your members. Okay, so with this ones right here taken into consideration, guys, the first thing that we would be doing is that we will be assigning our load details already, or our load cases already. So for our load cases, guys, what you would be doing is that you would be clicking at this tab right here, which is loading. So click loading right here, and this interface would come out. Then after which, just click in this load case detail right here, then press add. And this interface right here would come out, but I would be erasing everything first. Okay, so there. And take note, guys, that if you have earthquake loads into your structures, you must define them first before defining anything else. So with that, guys, I would be choosing seismic H right here. This indicates that your seismic load is to be a horizontal one. So horizontal seismic load. And let's say that I would be naming this, let's say, earthquake. So EQ, and I want it to be acting at the positive x-axis. So EQPX. So as per the nomenclature, it would be up to you, but I want it this way. So click add, and as you can see here, I already have my earthquake load directed at the positive global x-axis. And if that is to be our first load, then our second load is to be the earthquake load directed negative x-axis. I mean, towards the negative global x-axis. So add, and I would be doing the earthquake load towards the positive z-axis and the earthquake load towards the negative z-axis. So add. Then after which, since I have already defined all of the earthquake loads here, the next load case that I will introduce is, of course, your dead loads. I want it to be DL, or let's say if you want it to be dead load, but of course I want it just to be DL. Then click dead right here. So this is for your dead loads. Press add. Then lastly, I want to include my live loads here. So live loads. So this is for live load and this is for roof live. So I would just be clicking live load, then press add. Okay, so now that I already have my load case details here, the next thing that I will be doing is that I will be getting the magnitudes of the loads that I will be assigning into our structure. Okay, so these are to be the loads that we will be transmitting into our structure. So for your dead loads, guys, we would be putting concrete hollow blocks, and we would also be subjecting it with ceiling loads, floor finish, and the 125mm thick concrete slab. Okay, so there, and if you can remember our plan before, it is to be like this one right here. So this is to be our loads. So in our example here, guys, our external loads, or let's say our external walls, which is to be these ones right here, the ones that are drawn in with blue ink or a blue line. So we would be subjecting it with the loads indicated here. So this one right here is to be for your exterior walls. This 6 inches CHB plastered both face. And this 4 inches CHB right here is to be placed as your interior walls. For our example, guys, these are to be for your interior walls. So this one right here. So this is your interior walls, the one highlighted in yellow. So, okay. So, there. So once again, the first thing that we will be doing here is that we will be solving the magnitude of these particular loads right here. Okay, so going back here. So the 4 inches CHB plastered both face. So what is to be its weight? So we would be going to Table 204-1 in the National Structural Code of the Philippines. As you can see here, guys, my reference for these load pressures is to be the National Structural Code of the Philippines 2015 edition. So I would skip straight to Table 204-1. So it would be this particular table right here. Oops, I mean 204-2, I should say. So this is for the concrete masonry units, or the CHB. And as you can see in this part right here, guys, so 4 inches CHB plastered both face. So this 4 inches right here is to be the thickness of your hollow blocks. So it would be this ones right here, because 4 inches is approximately 100 mm. So if you would be converting 4 inches into millimeters, that is approximately 100 mm. And I will assume that the installed concrete hollow blocks in this project is to be a fully grouted one. So it is either this one right here, this one right here, and this one right here. And for the sake of our computation, I will assume that it is to be this one right here, or the heaviest one. So 2.84 kilopascal. So I would just be writing them here. So 2.84 kilopascal. So this one right here is to be in terms of kilopascal. But it is indicated here that it is to be plastered both faces. And if you would be looking at this portion right here, you would be adding 0.24 kilopascal for each face plastered. And if you have two faces, then it means that we would be adding 2 times 0.24 kilopascal to this particular load right here. So with that, guys, this is now to be equal to, so equal to 2.84 plus 0.24 times 2. Since we would be having two faces. So a wall has two faces, that is to be the interior side and the exterior side. So that is for this particular load right here. So that is now to be 3.32 kilonewtons per square meter. And as for your 6 inches plastered both faces, it would now be this one right here. So this is for your 6 inches right here. So this is for your 6 inches. So if I would be bringing out our calculator, so for a while guys. So if I would be converting 6 inches into millimeters, so 6 times 25.4, and that is to be approximately 152 mm or 150 mm if you would be rounding it off to the nearest whole number. Okay, so it would be at this column right here once again, and for the sake of our computation, I would be assuming that our load is to be this one right here, or 2.97, or the heaviest among them all, to be much more conservative. And once again, we would be plastering it both faces, so we would be adding 0.24 kilopascals to both faces, so times 2. So with that guys, this is now to be equal to, so equal sign 2.97 plus 0.24 times 2. So this is now to be its load for the concrete hollow blocks. So there, and now that we are done with the walls or the wall loads, the next thing that we will be solving is for the ceiling loads. So for your ceiling loads, it is indicated here that we will be using acoustical fiber board, mechanical ducting, and suspended channel system. So using this same table right here on your right, we would just be scrolling to the left and upwards. So this is for our ceilings. So for your pressures guys, we would be making use of this one right here. So acoustical fiber board, this one, and we are to use mechanical ducting here. So we would be having mechanical duct allowance and suspended steel channel system, and it is to be this one right here. So what you will be doing here is that you will just be adding the three of them. So from that guys, I would just be writing them here at this Excel file. So equal sign 0.05 plus 0.2 plus 0.1. So that is 0.35. And if you don't believe me, then let's use this calculator right here. So 0.05 plus 0.2 plus 0.1, that is now to be equal to 0.35. So that is to be this particular load right here. Okay, and after which guys, what we would be doing is that you would be solving for the floor finish here. So in this building right here, we are to use 25 mm, ceramic tile on a 25 mm mortar bed. So once again, using this PDF file right here, or this National Structural Code of the Philippines, we would now be searching for this particular ceramic tile right here. We would be using this one right here. So ceramic or quarry tile on a 25 mm mortar bed. So we would be making use of this particular load right here. So just 1.1. So this is now to be 1.1 kilonewton per square meter. And as for your number 4, so this is now to be the weight of the concrete slab. And it is indicated here that the concrete slab is to be 125 millimeters thick. And we are to assume in this one right here that the unit weight of reinforced concrete is to be 24 kilonewtons per cubic meter. And for us to get the pressure, what we would be doing is that we would just be multiplying it by the thickness of the concrete slab. Okay, so with that guys, so once again, unit weight, which is 24 kilonewtons per cubic meter, we would just be multiplying it by the thickness of the concrete slab. And as indicated here, our thickness is to be 125 mm. So 125 mm in meters is equal to 0.125 meters. So meters would cancel out, so that would just give you an answer in kilonewton per square meter. There. So we are now done with our dead loads. So the next up is for live loads. So for your live loads, you would go to table 205-1. So it is to be this one right here. So this is to be your table 205-1. So once again, this building right here is to be a residential building. So if this is to be a residential building, we would go straight to number 15 here, or this is for your residential buildings. So this one right here. So for the basic floor areas, or let's say your bedrooms, your kitchens, your living rooms, and whatnot, we would be using 1.9 kilopascal. So I have already indicated them here. So 1.9 kilopascal. So for your exterior loads, you would be using 2.9 kilopascal. So this is for our roof decks later on. So this is already typed in this Excel file right here. So this is to be your 2.9 kilopascal. Okay, so there. And for our seismic load definitions, guys, I would be typing them here. So for our seismic loads, of course, our location is to be in Baguio City. So this is to be our basis for this particular values right here. So for your NA, so I'm sorry, this should be our near source factor. I would just be erasing it. Near source factor NA and near source factor NV. So this are to be it. So for our seismic zone factor right here, guys, so what zone does it belong? So if you have already watched our previous pre-recorded video lecture, here in the Philippines, we only have two zones. So if it is located in Palawan, that is to be zone 2. And if it is located at the right part of the Philippines, that is to be in zone 4. So I would just be showing you here. So for a while. Okay, so these are to be our seismic zones right here. So if your structure is to be located at this portion of the Philippines right here, it means that you are in zone 4. Otherwise, you are in zone 2. And since Baguio City is to be located approximately here, it means that it is located at zone number 4. Okay, so for your zone number 4, guys, your seismic zone factor is to be equal to 0.40, which is to be this one right here. So if you are wondering where this one right here came from, it came from this table right here, which is 208-1. So once again, our residential building is to be a standard occupancy structure. So meaning that we would be using this one right here. And if your facility is to be an essential facility, you would be making use of this one right here. So as per the definition of this ones right here, or this occupancy categories right here, it is already in the National Structural Code of the Philippines. So you better read it. Okay, and as for your structural system, or right here, this is to be located at table 208-11. So I would just be skipping straight there. Okay, so this is to be table 208-11A, or this is to be for the values of R for your structural systems for concrete. So once again, this is just for concrete. And since we are to design this one right here as a special moment resisting frame, we would be making use of this particular value right here, which is 8.5. So if you cannot read this one right here, so this is for your special moment resisting, special reinforced concrete moment frame. That is now to be 8.5. Thus, 8.5. So for our near source factor NA right here, this is from table 208-5. So I would just be going straight there. So 208-5. So this is to be it. So your near source factor is to be dependent upon the location of the site to the nearest fault line. So I have already plotted the nearest fault line here. So this, let's pretend that our structure is to be located at this one right here. And the nearest source, the nearest fault line is to be tubaw fault, which is located here. And according to the GPS here, it is to be 2.8 kilometers from it. So this one right here, or this blue line right here, is to be 7.8 kilometers. And if you would be looking at the portion on your right, or the stable on your right, and it is to be greater than 5 kilometers, but it is to be less than 10 kilometers. So there. And from that, guys, you can either interpolate these ones right here, so 1.2 and 1.0, but it would be much more conservative if you would just be using 1.2 right here. So with that, guys, I will be making use of 1.2 as our near source factor NA. So this is now to be 1.2. And for our near source factor NV, it is to be this one right here. Oh, by the way, I did not tell you a while ago that I chose this one right here from these two, because since this is to be the Tubao fault, or in Baguio City, its seismic source type is to be seismic source type A. So there. And for, once again, for your near source factor V, it is either that you would be interpolating from these two right here, but it is better for me if I would just be choosing 1.6. So I would just be choosing this one right here for me to have a conservative value. So this is now to be equal to 1.6. Okay, so those are to be the values that I need. As for this CA and CV right here, or the seismic coefficients, since it is already dependent upon these values right here, we don't need to get these ones right here later on. So I will be showing you later why these ones right here are already not needed. So okay, so we are already done with our load analysis. So the next thing that we will be doing is that we will be assigning them into our structures already. Okay, so the next thing that we will be doing right now is that we will be assigning the loads into the respective members, or the structure itself, in this load case details right here. And I will be assigning the live loads first before going on to the next, for you to have an idea how it works. So if I would be doing that, just click on your load cases. So I would be clicking on this load case right here, which is for your live loads. Then click add right here, and this interface would come out. So it would ask you on how is the load to be transmitted into the structure itself. So is it a self-weight load? So this self-weight right here is fairly self-explanatory already. This is just the weight of your structural system, which comprises of the beams and the columns. So this is for your nodal loads right here. So once again, self-explanatory, that these loads right here are to be subjected directly to your nodes. So there, and we also have your member loads right here. So in your member loads, you can have a uniform force, a uniform moment. So as for your uniform force right here, this is to be your linear loads. That is to be in terms of kilonewtons per meter and whatsoever. Okay, and we also have this ones right here. So we also have your fixed end, concentrated force, concentrated moments, and whatsoever. Okay, and we also have our physical member load right here. So what is to be the difference between your member load and your physical member load? So the difference is that for your member loads, these are to be subjected in your analytical models. So if I would just be hiding these two right here. So as you can see, we are modeling analytically. So this one right here is to be an analytic model. So we would be making use of this. But if you have a physical model of your structure, you would be making use of this. So once again, we would be making use of our member loads for this particular video lecture since we have an analytical model. So there, and we also have your area loads, your floor loads, plate loads, seismic loads, time history, and whatsoever. But for your live load, since as you can see at the left part of your screen, so this is to be our live load right here. So this is to be our live load. So they are to be in terms of kilonewton per square meters. And those pressures are to be transmitted into our structure in the form of a floor load. So it would be this one right here. So this is for your floor load. So once that you would be clicking this, you would be welcomed by this interface right here. So in this particular interface right here, you can assign your floor loads using your X range, your Y range, your Z range, or your group. And it is better if you would just be assigning the groups of your members first or your floor members first before applying them here. Okay, so with that, guys, I would go here. So I would just go to the top view of it. So top view. So as you can see, this is to be our plan. So this is to be our plan view. But by the way, guys, before anything else, if you notice here that I have introduced these beams right here, I am assuming that this is for your stairs. So at this particular view, I will be assuming that the bottom of the stairs is to be located here and the top of the stairs is to be located here. So that is per floor. So for this floor right here, this is to be the top of the stairs and this is also for the top of the stairs. So this model right here or this members right here were not introduced in the previous video lectures. I have just introduced them now. Okay, so once again, going back to the task at hand. So by the way, I would just be choosing these floors right here. So for a while. Okay, so these are to be your floor areas. And this is to be its plan view and these are to be its beams. So this is to be your exterior beams right here, and this is to be for your interior beam. So this is to be our plan at your lower right part of the screen, except that we now have this additional intermediate beams right here. Okay, so if you can remember from your reinforced concrete design that your slabs is to be categorized into two. So the first one is what we would be calling your one-way slab and the second one is what we would be calling your two-way slab. One-way and two-way slab. And they are to be given by these limits. So for your one-way slabs, guys, if you would be dividing the short dimension, so short divided by the longer, this should be less than or equal to 0.5. And if not, so if let's say your short over longer is to be greater than 0.5, it means that you have a two-way slab. So that is to be it. So for example, that this one right here is to be 1.8, as you can see here, and this one right here, this node-to-node distance right here is to be 4.0. So if we would be getting our calculator here, so I would be putting them to our right first. So 1.8 divided by 0.4, that is now to be equal to 4.5. So meaning that this slab right here, so this slab right here is to be a one-way slab. So one way. It is same with this. So this is also one way and this is also one way since all of them have the same dimensions. And as for this one right here, so I would be measuring it. So what is to be the node-to-node distance of this? So from this point up until this point, this is to be 3 meters. I'm sorry. So this is to be 3 meters right here. And this one right here is to be 4 meters. So this is to be 3 by 4. So 3 meters by 4 meters. So if I would be dividing it, 3 meters divided by 4 meters, and that is now to be equal to 0.75. And since it is greater than 0.5, we can say that this particular areas right here are two-way slabs. So two-way. So two-way. So together with this one right here, this is to be two-way. This is to be two-way. And this is also to be a two-way slab. So two-way. And as for this portion right here, guys, if you can remember, this is to be hollow since this is to be the location of your stairs. So there, so two-way, and this is to be a one-way slab. This is also one-way. Then one-way, and one-way. So for your one-way slabs, let's say that you will be subjecting this into loads. So your loads are to be transmitted in this manner. So this is to be the load distribution of it. So these beams right here or the longer beams would just be the one that is to be subjected with loads. However, for your two-way slabs, the loads in the two-way slab will now be distributed in all of the beams. So all of them would have their share. As per our one-way slab right here, only these beams right here are assumed to be subjected with loads. So that is for our one-way and two-way slabs. So with those taken into consideration, we will be grouping our beams here as one-way and two-way slab. Okay, so now that we already know which one of these ones right here are for your one-way slabs and two-way slabs, the next thing that I will be doing is that I would now be grouping them. Okay, so I would go from floor to floor. So I would maybe start with the roof decks first. So let's say that this is to be the 1, 2, 3, 4. So let's say that this is to be our fourth floor or our roof deck. So I would be isolating them first. Then I would go to the top view. So for your two-way slabs, we have already known earlier that these are to be for your two-way slabs. So this one's right here. So what I would be doing is that I would be grouping them. So if you would be grouping them, press Control G in your keyboard. So Control and G. And once that you will be doing that, this interface would come out. So you would be defining the group name. So let's say that this is to be for your roof deck. So RD2 way. So let's say RD2WAY. So let's say that is to be its group name. Then select the type, and this is to be a floor type. Then press OK. Then once that you already have this grouping right here, so press associate this time. Okay, so next up for your one-way slab. So these are to be your one-way slab. So this one right here, this one right here, and this one right here. So make sure to not include this beam right here, since this one right here is to be hollow. So okay, so once again, just select this one right here, this one right here, and this one right here. So this is for your one-way slabs. So I would be creating a new one. Let's say RD one-way. Then its type is to be floor. Then press OK. Oops, one way I should say. So one way. Then press OK. Then associate to selected geometry. So that is for this group right here. So next up, let's go with the third floor, which is to be this one right here. So I would be isolating this. So select and view selected objects. And then I would be viewing its plan view. So it would be this one right here. So same old, same old. So just select this ones right here and assign it to be a two-way slab. So I would be creating once again, and let's say that this is to be a third floor. So 3F 2-way for pretend. So two-way. Then this is to be a floor. Then I would be creating another for our third floor. One way. So TF one way, then press 4. Press OK. Then we will be assigning what needs to be assigned. So this is for your two-way. So associate to selected geometry. And for our one-way, once again, we would be selecting all the one-way slabs. The beams that are connected to those one-way slabs. So this is to be it. So 3F one-way, associate to selected geometry, then associate. So I'm not quite sure if you saw, because I just noticed now that my Excel file is to be in the way. So I would be hiding them first. So there. So once again, I assigned this one right here to the two-way slabs. So I selected them here. So I selected this one here. And I assigned this one here in these slabs right here. So that is for our third floor. So let's go straight to our second floor. So same old, same old. So click them, selected object. Then I would be going to the plan view or the top view. Then I would be creating a new one. Let's say that this is to be 2F 2-way. So this is to be the two-way slabs for the second floor. Then floor. Then I would be creating another one. So 2F 1-way. Then floor. Press OK. So for the two-way, so same old, same old. This is to be for your two-way. And this one right here is to be for your one-way. So one-way. So there. And now that I have grouped all my beams already, I would be displaying all of the structures already. But if you are wondering why am I not grouping these ones right here, is because that I would not be subjecting these beams right here with loads because they are already in the ground floor. So with that, guys, I am assuming that the loads in the ground level would be directly transferred onto the ground since this is to be your ground level. But it would be upon the judgment of the engineer if he or she would want to assign floor loads in the ground floor level. But in my case, I wouldn't be doing that any longer. Okay, so once that you have already created your groups, so I would just be pressing X right here and I would be displaying our Excel files once again. So for us to subject this ones right here, I mean the loads right here with the live load, so just click on your LL right here. So click live load, then press add. Then go straight to our floor loads right here. So this is for your floor loads. Then click group. Then I would be assigning the live loads at the roof deck two-way. So click that, and as you can see at the Excel file to your left, for your exterior loads, this is to be 2.9 kilonewton per square meter. So I would be applying 2.9 kilonewtons per square meter here. But take note that this should be negative since its direction is to be along the global y-axis. So for your global y-axis, the positive y-axis is to be upwards and the negative y-axis is to be directed downwards. So I would be clicking add. So there, and for our roof deck one way, so just click in this part right here and you wouldn't be changing the load since the pressure is to be directed vertically downwards. But this time, just tick this box right here, which says one-way distribution. So click that, then press add. And for our third floor two-way, we would be subjecting it with this load right here, which is 1.9, since our third floor is already interior. Okay, so I would be changing this. So negative 1.9, then I would be removing the one-way distribution since this one right here is to be a two-way slab. So press add. Then as for this, so for our one-way slab right here at the third floor, so just click this one right here, one-way distribution, then add. Then for our two floor once again, I mean the second floor, I should say, that is to be a two-way slab. And as for this one right here, this is to be a one-way slab. So press add. And once that you would be doing that, these are our loads right here. So if you would be clicking it, you can see that our loads are now properly assigned to each of these floorings right here. So if you want to change the scaling of your loads here, so let's say that this scaling right here is very big. So you can just go to view, then go to label settings, then go to skills right here. And for this distributed force, so if you would be increasing this sizes right here would decrease. And if you would be decreasing this, your size right here would now increase. So let's say that I would be pressing 10 here, then I would be pressing apply. The sizes have diminished. So if let's say I would be pressing 0.5 here, then press apply, and the scaling of the loads would be as follows. So I think I want my scaling to be 5, just 5. So 5, press apply, then okay. So the scaling won't affect the analysis later on. So they are just for our graphical interface. Okay, so that is how you would be assigning floor loads. Okay, so the next thing that we will be doing here is that we will be assigning our dead loads, our earthquake loads, and whatsoever. So let's go from case to case. So right now, we would be assigning our earthquake loads or our EQPX right here. So I would be clicking this, then I would be pressing add. And after that, as you can see, well, of course, you would be going straight here in seismic load. So if you would be clicking here, it is said here that seismic definition is required in order to assign a seismic load. So how can we do that? So just click close right here, then go in your seismic definition right here, then press add. So there guys, here in STAAD, you do not need to manually compute for the base shear to be inputted since the formulas in the NSCP is already incorporated in STAAD. Since the reference code of STAAD, the reference code of NSCP in earthquake loads is to be UBC 1997, which is already included here. So UBC 1997. So it would be this one right here. Okay, but before everything else, guys, we must first take note that before applying our seismic loads, we must apply diaphragms into our structure first. But what is a diaphragm in the first place? So what is to be the use of a diaphragm? So let's say that we will be having a certain lateral load here. So let's say that it is to be directed here at this particular point right here. So what a diaphragm does is that a diaphragm would distribute or would transmit your lateral load to each of the vertical resisting element of the structure. So with that taken into consideration, guys, so I would just be going to our top view right here. So once again, this is to be a top view. And let's say that we would be having a certain lateral load directed here. And with the presence of a diaphragm, so your diaphragm would now be transmitting this load right here to each and every vertical resisting element in your structure. And since this is to be a special moment resisting frame, our columns are to be designed that they are to be the one resisting these lateral loads. And since this one right here is to be your column right here, so this is to be your column. So these are to be your columns and etc. So all of these joints right here are columns. Your diaphragms would now transfer this particular load right here to each of these columns. So they are now to be resisted by these columns right here. So this one, and whatsoever. So there. So in your structures, guys, your diaphragms are that of your floor slabs. So in this case right here, our diaphragms are to be for your floor slabs. So there. So I would just be erasing them first, and let's go back to our structure. For us to assign diaphragms, just click here on the specification tab right here, then go to nodes. So once that you will be clicking nodes, go to floor diaphragms, and for your diaphragm number 1, you would just be specifying the height of that particular level. And if you can see here, which I could not, so I will just be displaying here our dimensions. So node tools, node to node distance. So this is to be 1.8. This is to be 4.8. This is to be 7.8. And from this point up until your top floor, that is to be 10.8. So that is to be 1.8. This is to be 1.8 meters. This is to be 3 meters, 3 meters, and 3 meters. Okay, so with this ones right here taken into consideration, what we would be doing once again is that we would be clicking node, go to our floor diaphragm right here, and we would just be specifying the floor levels that we want to introduce the diaphragms. So we want to introduce the diaphragm in the first floor level, and that is to be at an elevation of 1.8 meters. Then click add. Let's create another one. So floor diaphragms, then the floor level is now to be equal to 4.8. So this is to be it. And another one that is to be at a level of 7.8. So this is now for your third floor. So 7.8, and click once again. And for your diaphragm right here, this is to be 10.8, or this is for your roof deck already. So press add. So once that you have defined the diaphragms already, you don't need to assign them since they are already automatically assigned. So as for this one right here, I would be highlighting it. So as you can see that all the nodes at the first floor level are already highlighted. So if I would be clicking here, as you can see, all the nodes at the second floor level are now highlighted. So they are already automatically assigned. Okay, so there. Okay, so going back to our loading, so let's go once again to our seismic definition. So click definitions, then click seismic definition right here, then press add. And once again, like what I have mentioned earlier, that the reference code of the National Structural Code of the Philippines is to be UBC 1997. So that is for seismic. So UBC 1997. So click here. And you would just be changing these parameters right here. So once again, here in STAAD, you do not need to manually compute for the base shear to be inputted here, since the formulas in NSCP are already incorporated here. So if you would be changing these parameters right here, STAAD would automatically solve for the base shear already. So looking at the Excel file to your left, so these are to be the seismic load parameters that we will be inputting here. So for our zone, since we are in zone 4, this is now to be equal to 0.4. And for our importance factor, that is to be equal to 1. And for our RW, this is to be 8.5. Same is true with our RWZ. This is also 8.5. And for our soil profile type, so we did not include any soil profile type here. So if I would be displaying our PDF file or our National Structural Code of the Philippines, by the way, I would just be increasing the size here. So it is stated here that when the soil properties are not known in sufficient detail to determine the soil profile type, type SD shall be used. So we will be making use of type SD here. Since, once again, in the Excel file to your left, we have not included the soil profile type here, we are to assume that our soil profile type is to be SD. Okay, so with that, guys, since our soil profile type is to be assumed SD, SD is to be number 4 here. So number 1 is SA, SB, SC, and this is to be SD, which is number 4. Okay, and as for our near source factor, once again, looking at the Excel file to your left, our seismic near source factor, that is now to be equal to 1.2. So this is to be 1.2. And our near source factor is to be 1.6 or NV. But what about for our CT? Looking once again to the PDF file to your left, I would go to equation 208-12, which is this one right here. And it is indicated here, for us to get the value of our T, we would be needing the value of our CT, which is to be this portion right here, or the CT value. So for our CT value, since our structure is to be a reinforced concrete one, the value for our CT would be 0.0731, which is to be this one right here. So I would be typing 0.0731 here. So I'm not quite sure if you can read what is indicated at the upper left portion, but if not, I would be increasing the size first. So there, we would be making use of 0.0731, since our structure is to be a reinforced concrete moment resisting frame. Okay, so there I would be putting this back here. So there, and if you want to override the period here, you can also do that. You can also make use of this particular equation right here and overwrite it. But if not, guys, STAAD would automatically compute for the period in the X and Z directions. So I would now be pressing add. Okay, but by the way, guys, we have a catch here in STAAD. Because here in STAAD, it would assume that the location of the base shear is to be located at the nodes that is to be at the lowest elevation. So in this case, guys, the location of the base shear is to be located at the footing level. Let's say that this is to be your side view. STAAD would assume that the location of your base shear is to be at this particular location right here, or the lowest elevation of your structure. But for pretend that you would be having a certain land geometry in which that this is to be your ground level right here. So let's say that this is to be your ground level right here. So let's say that that is to be your ground level. The correct location of your base shear is to be located here. This should be the location of your base shear, or this one right here. So there. However, once again, STAAD would always assume that the location of your base shear is to be located at the lowest nodes of your structure. So what do we do now? So we have two approaches here. So the first approach is for us to delete these ones right here. So we would be deleting all of these nodes right here so that the lowest elevation of our structure is to be located at this portion right here, or this one right here. We want STAAD to think that way. So that's the first approach. And the second approach is for us to leave it as is. So with that way, guys, we are to assume that the base shear is to be located here. And with that, guys, we are assuming that this soil profile right here, so once again, this is to be your soil. We are assuming that this particular soil right here is incompetent for the base shear to be transferred at this particular location right here. With such, guys, the value of our moments here would now be much more conservative. So if you want a more accurate work, it is better for you to delete substructures right here for STAAD to assume that the base shear is to be located at this particular portion right here. Or you can just go with this approach wherein the base shear is to be located here. So this would give you a much more conservative value. So once again, if you want to have a conservative value, go with this approach. And if you want to have a more accurate value, just delete these nodes right here. So delete this node, delete this node, this node, this node, and whatsoever. But in my case, guys, once again, that I will be assuming that the soil here is to be incompetent enough for it to transfer the base shear at the ground level. So here. So I wouldn't be assuming it that way. I would be assuming that the base shear is to be located here. So I wouldn't be deleting any members here. Okay, so if you notice that the equation that we will be using for the design base shear will be this one right here. So look at the upper left corner of your screen. So this is to be the design base shear of our structure. So if you cannot read that, I would just be writing them here. So that is to be given by the equation of V, or the design base shear, is to be equal to CV times I, or the importance factor, divided by RT times W. And if you can notice, guys, that all of these parameters right here are already indicated in the seismic load definition, except for this load W right here. So this load W right here is actually the total weight of your structure, or in other words, it is to be the total dead load. And for us to include the total dead load in our seismic load definition, you can just do this. So click here, then press add, then of course include the dead loads that you want to be included. But if you can remember, guys, we also need to define our dead loads at this portion right here. So if you would be defining your dead loads here, you would once again define your dead loads here. So you would be doing it twice. And what we would be doing here right now, for us to avoid redundancy of the definition of the dead loads, what we would be doing is that we would be making use of this reference load definition right here. And once that we have already indicated our dead load here, we can refer to it. We can repeat the load for our seismic load definitions and for our dead load per se. Okay, so with that, guys, I would be clicking here, then press add. Click add. Then after which, just click here. So dead load. So dead load, then let's say reference load, reference DL, for example. So with that, press add. The next step will be similar to what we have been doing in our live loads earlier. So just click here on the reference dead load, press add, click add, then of course include every load that is under the load case of your dead load. So of course we want to have our self-weight load right here. So for the self-weight load, once again, this is to be the weight of all of these members right here. So that is to be the weight for your beams and your columns. So I would just be pressing add here, and make sure that its direction is along the y direction and its factor should be -1 for it to be going vertically downwards. So I would just be pressing add here. Then as for the other ones, so looking at the Excel file to your left, these are to be the pressures that we would be assigning. But by the way, guys, I forgot to recompute this. So as you can see, for your 4 inches CHB hollow blocks and for your 6 inches CHB hollow blocks, they are to be in terms of kilonewtons per square meter. But as you know, that this loads right here would only be carried by these beams right here, what we would be doing is that we would be getting its line load. And for us to get its line load, what we would be doing is that we would be multiplying these pressures right here by the height of the walls. And that these beams right here, I mean these nodes right here, the node to node distance or the floor to floor distance of our floorings is to be equal to 3 meters. So are we going to multiply it by 3? The short answer to that is no, since we already have our beams here. So if I would be viewing its 3D rendering view or its 3D section, so if I would be applying it, so once again, the floor to floor distance is to be equal to 3 meters. So that is to be equal to 3 meters. And if we would be going back here to the properties tab, we have, I have assigned before that the depth of the beams is to be 400 mm. So it would be this one right here. So 0.4 mm. So meaning guys, if we are to go back here, so I'm sorry. So I would just be erasing this first. Then I would go once again to the 3D rendered view. So once again, this area right here, this dimension right here or the floor to floor height is to be equal to 3 meters. So 3 meters. So meaning that if this one right here is to be 0.4 meters, so 3 meters minus 0.4, that would give you an answer of 2.6. So meaning that this dimension right here is to be equal to 2.6 meters. With that, what we would be doing is that we would be multiplying these dimensions right here, this pressure right here, by 2.6 to arrive at an answer in terms of kilonewtons per meter or a linear load. 3.32 times 2.6 meters, and that would give us an answer of 8.632 and 8.97 respectively. So if I would be showing you my calculator, which is this one right here, so that is basically 3.32 times 2.6, so that is now to be equal to 8.632, and 3.45 times 2.6, that is now to be equal to 8.97. So they are as follows. So this is to be in terms of kilonewton per meter already. So they are to be member loads. Okay, so there. So what do we do now? So the next thing that we will be doing right now is that we will be assigning them into our structure already. Okay, so for our ceiling loads, so I will be assigning our ceiling loads. No, I think it is better if you would just be getting the total of these three. So the total of that three, so that is to be equal to the sum of these three right here. So that is to be 4.45, or using our calculator to your right, that is to be equal to 0.35 plus 1.1 plus 3. So that is to be 4.45. Okay, so there, 4.45. So this is to be the dead load that we will be applying to each of our slabs. So let's just go to define, then reference load definition, then click on your reference DL, then press add. Then we will be adding floor load of 4.45. So negative 4.45, and choose the group. So I would be assigning them to all of this. So add RF two-way, add to F two-way, add, and as for the one-way slabs, so click one-way distribution here, then assign it here, assign it here, then assign it here, then press close. So these are to be your dead loads here. So as for this self-weight right here, guys, you must assign this first to all of the members. So it is either that you would be clicking all of the members, then assign to selected beams, or better yet if, better yet if you would just be assigning it to view. So assign to view, press assign, then the self-weight of all of the members right here right now would now be included into our dead loads. Okay, so what else what else are we missing? In the wall loads. So what I would be doing right now is that, of course, I would be assigning our loads right here. So I would be clicking this. Then I would be isolating it first. So view selected objects. Then I would be going to the top view. In the 6 inches hollow blocks right here would now be your exterior load. So meaning that they are to be subjected to our exterior beam. So it would be this one right here, this one right here, this one's right here, and this one's right here. So I would be I would be adding a new load. So add new load. So by the way, I think it is better if I would just be selecting both of these floors right here. So I would just be selecting this and selecting this, so that if I would be viewing them, and if I would be going to the top, and let's say that I will be selecting the exterior beams, which are to be these ones right here. And if I would be going to the isometric view, as you can see, both the third floor and the second floors are already selected. And with that, guys, I would now be adding a load. And since this is to be a linear load, we would be adding a member load right here. And that is to be a uniform force. And our uniform force for our exterior walls is to be 8.97 as indicated at the Excel file. So this is now to be equal to negative 8.97 kilonewtons per meter. And make sure that they are along the global y direction, which follows this orientation right here. So positive y is going upwards. So meaning, since this is to be a gravitational load or a gravity load, we should include negative here for it to be vertically downwards. Then I would be pressing add. So once that this is already defined, what we would be doing is that we would be assigning it to the selected beam. So click this, then click assign to selected beams. So assign. So as you can see, we already have loads in our exterior beams. Okay, so for our interior beam, so I would go here once again. So this is to be for the wall loads. So let's say that these are to be your walls. So let's say that our walls are just to be these ones right here for pretend. So add, so click here once again, click add, then member loads. Then looking at the Excel file to your left, this is now to be equal to negative 8.632. So this is for your 4 inches CHB hollow blocks. So click add, then I will be assigning this to selected beams. Okay, so there. So the question is, are we done? So basically, if we are to check the Excel file, we already have assigned all of the dead loads. But we forgot the stair load here. So for your stair loads, or for the loads of the stairs, what you would be doing here is that you would be getting the total weight of the stairs by multiplying its total volume by 24 kilonewton per cubic meter. Then you will just be assigning them to the beams concerned. And in this structural plan right here, I am to assume the stairs is to be oriented like this. So it is to be this one right here. So this is to be the stairs, and this is to be the stairs. So as you can see, guys, it is to be carried by this particular beam right here and this beam right here. So that is for the stairs from the third floor going to your roof deck. And for the stairs going from your second floor to your third floor, it would be carried by this beam right here and this beam right here. So I would just be isolating them for you to see it better. So it would be this one right here, this one right here, this one right here. Oops, I'm sorry. And this one right here, and this particular beam right here. So I would just be isolating them. So it would be this one. So this is to be the top of your stairs. This is to be your bottom of the stairs. This is to be the top of your stairs. So this is to be your stairs. What we would be doing here is that we would be getting the total weight of the stairs by multiplying 24 kilonewton per cubic meter to the total volume of the stairs, and that we are to assume that its load. So let's say that this is to be the total weight. So let's say that this is to be the total weight, for example. So let's say that that is to be the total weight of our stairs. So let's say that that is to be W. And this W right here is to be carried by this beam right here and this particular beam right here. And we are to assume that this reaction right here is to be equal to 1/3 the weight. So let's say W over 3. And we are also to assume that this particular support right here or this particular beam right here would carry W times 2/3 or 2/3 of the weight. So for example that our total weight, so for example that the total weight of our stairs is to be equal to 30 kilonewtons, just for pretend. So for example that this came from the total volume of the stairs times 24 kilonewtons per cubic meter. So its total weight is now to be equal to 30 kilonewtons. So meaning that this particular beam right here is to be carrying 1/3 of 30 kilonewtons. So 1/3 times 30 kilonewtons. So this is now to be equal to 10 kilonewtons. So this is to be 10 kilonewtons. And as for this one right here, this is to be 2/3 times the weight, which is 30 kilonewtons. So this is just my assumption, guys. So if you have a better computation, then you can use those. But if you don't have one, you can use this rule of thumb right here. So 2/3 times 30 kilonewtons, this is now to be equal to 20 kilonewtons. So 10 kilonewtons and 20 kilonewtons. But take note, guys, that this dimension, right? I mean, this is to be a beam. So if we are to subject 10 kilonewtons here and 20 kilonewtons at this lower part, we must first distribute it to this whole length and convert it into a linear load. So from that, guys, I would just be showing the dimension of this particular beam right here. So nodes. So the node to node distance of this is to be equal to 1.5 meters, as you can see here. So 1.5 meters. So if this is to be equal to 10 kilonewtons, so let's say that this is to be equal to 10 kilonewtons, we will be dividing it by 1.5 meters for us to arrive at a certain load of kilonewtons per meter. Looking at the calculator to your right. So 10 divided by 1.5, this is now to be equal to 6.66. So this is now to be equal to 6.66 kilonewton per meter. So meaning that we would be assigning 6.66 kilonewton per meter in this particular beam right here. And as for this beam right here, so this is to be 20 kilonewtons. So we would be dividing this once again by 1.5 meters. And we would be arriving at an answer of, so 20 divided by 1.5, and we would be arriving at an answer of 13.33. So this is to be 13.33 kilonewtons per meter. Okay, so there. So take note of these numbers right here, guys. So 6.66 kilonewtons per meter and 13.33 kilonewtons per meter. Okay, so we would be assigning this to right here, to these beams right here as dead loads. Okay, so what I would be doing is that, of course, I would be defining it here first. Click here, then add your reference dead load, then go to member loads, then this is now to be equal to negative 6.66. So this is to be the top portion of the stairs. Click add, then add another, and this is to be 13.33. Then click add, and make sure that they are directed along the global Y direction. So click add. Okay, so the next thing that we will be doing is that we will be assigning this to our selected beams. Okay, so I would be selecting this. So this is to be the top portion of the beam. This is to be the top portion of the beam. and this is to be the top portion of the stairs, I should say. So there I would now be assigning this 6.66 right here. So assign to selected beams, then press assign, then click yes. And as for our lower portion of the beam, or I mean the lower portion of the stairs, so just click this one right here, this one right here. And as for this beam right here, which is located at the ground level, I wouldn't be selecting it any longer since I am to assume that the load would be transferred directly to the soil underneath it. So we wouldn't be designing this as a flexural beam. Okay, so there. So press this load definition right here, then assign to selected beams, then press assign. Okay, so now that you have defined our reference load for our dead load already, the next thing that we will be doing is that we will be repeating it for our seismic load definition and for our dead load right here. So for our seismic load definition, just click here, click add, then reference load. Then reference load, click on your reference dead load, transfer it here. Once transferred, click add. So meaning that this this reference load right here is already incorporated into our seismic load definition. So in your Excel file, in this particular equation right here, that is to be the value for our W. That is for the reference load Y. And as for this dead load right here, instead of repeating all of this, you can just click add right here, then repeat load. So repeat load, then reference load, then reference dead load, transfer it here, then press add. And with that, guys, you already have our dead load and our live load. So this is to be our live load, and this is to be our dead load. I think we are missing a couple of loads here. So by the way, I would just be re-adding our, I don't know why they are missing, but I would be adding our floor loads here. So group, second floor two-way, this is to be negative 1.9, add, and negative 1.29 one-way load. So there. So this is for your live loads, and this is for your dead loads. And for your earthquake loads, it would be as follows. So click here, then click add. Then go to seismic loads. Then in this one right here, so it is to be X direction, since this is to be the one selected. X direction, factor, positive 1. And are we multiplying factor for accidental torsion moment? So click this and click this one right here. So as for this one right here, press 1, and as for this one right here, 0.05. So this is for your natural torsion moment, and this is for your accidental torsion moment. So I would just be clicking add before I would be explaining it. So I would be explaining it right now. Okay, so what are those factors that I have included a while ago? So for example, that I would be going to the plan view. So let's say that this is to be your structure. So this is to be your particular structure. And the center of mass, let's say, is to be located here. So let's say that your center of mass is to be located at this particular portion right here. So the center of your mass is basically the centroid of the mass, or the mass centroid. And let's say that the center of rigidity is to be located at this particular portion right here. So your center of rigidity is to be the center of your resistance. So they are to be dependent upon the strength of your structural members and of course your diaphragm. So let's say once again that this one right here is to be your center of mass. And this one right here is to be your center of rigidity, for example. So as you can see, they have eccentricities. Oh, and by the way, your earthquake would approximately go through your center of mass. So let's say that this is to be your seismic load. So let's say that this is to be your seismic load. And this is to be your center of rigidity. You would be having a certain eccentricity right here. So this is to be your eccentricity. And force, so let's say that this seismic load is to be your force. So your force times your eccentricity, so you have your x and y eccentricities here. So you would be arriving at a certain moment. And that certain moment is to be a torsion in this case right here. So if we would be going back to our seismic loads here, so this one, so this case right here, or this moment right here, or our F times E, is to be your natural torsion moment. So we would be taking that into consideration. But what about for this accidental torsion moment? So according to the NSCP, if your center of rigidity, or this part right here, so let's say that this center of rigidity right here, it might move by, let's say, 5% to the left, right, and whatsoever. And with that, guys, we are to include it in our analysis. So for example, that the center of rigidity would move by 5%, then that 5% is to be this 5% right here. So once again, this is to be for your natural torsion moment. And as for your accidental torsion moment, that is to be accounted by the possibility that your center of rigidity would move. Okay, so those are to be it. So I would be closing this. And as for our earthquake towards the negative direction, then click add. Then go to seismic once again. So go to seismic load here. Then go to y direction. Then we would be applying -1 here, since we will be going to the negative x direction. So multiplying factor, this is to be 0.05. And this one right here is to be 1. Then add. So as per our z direction, so click add. Then of course seismic loads. Then right now we would be clicking z direction here, then +1. So this is still 0.05, and this is now to be equal to 1. Then add. Then as for our earthquake load in the negative z direction, so seismic loads, z direction, -1, this is to be 0.05, and this is to be 1.0. Then click add. With that, guys, we are already done in assigning our earthquake loads, dead loads, and our live loads. So there.